Thank you. Hello, everyone. Today we're going to understand how we can investigate the Earth, how we can read it, what are the major investigation layers that we need, uh, what do we expect, what kind of information we get. All these topics are going to be discussed in this webinar. No further ado, I'd like to acknowledge you. Now, the way we probably understand the human body or to investigate a human body is the same way, like in concept, of how we investigate Earth. So, you might say, I have kind of pain, or you might have swelling in your finger, and you would ask yourself, is it maybe strained tendon, strained muscle, or maybe fractured bone? But you cannot really tell because from my own experience, like once I had finger injury, and then I was discussing it with myself, and my conclusion was that I had strained tendon, but thankfully it was just small strain in the finger's muscle. So that's the first thing we do in our human body. We do correlation based on pain, based on, for example, the surface changes, like skin color changes, and this kind of stuff. Then we might go further and do X-rays, right? Because if you have anything finger injury or if you have anything related to your bones, you cannot have kind of like judgment without doing X-rays, right? So you're gonna do X-rays, which are directed to your body, and then they like differentiate between the soft and the hard tissues, like between your bones and between your soft tissues, right? And of course, we region. So I have like third of you, but you gotta these fingers, not finger any injury, right? Because you have soft tissues, you have a lot of tendons, ligaments, you have muscles. A lot of things are like squeezed in very tight zone. So what you're gonna do is probably doing MRI. Um, have better vision. It is not only differentiated between hard and soft tissues, it is also differentiating between different types of soft tissues like tendons, muscles, ligaments, and so on. Maybe then maybe you need to understand.
I'm sorry, you the voice disappeared. Yeah, I cannot hear you for now. Maybe I come back in a second.
Yeah.
Like I.
Can you hear me?
Okay, now it works.
Yeah.
Now it works.
Okay.
Yes.
Thank you for telling me. Okay. So as I've been saying, we sometimes go further and we do PET scanning that like shows us the functionality of your brain. Makes sense, right? And that's what we do. That's what we do generally
to understand Earth. Instead of doing X-ray and MRI, we do same kind of investigation. We have layers of investigation, and based on that, we make judgment. Also, for example, we might have intraoperative scanning. So while we are doing surgery, we're gonna scan. We do the same thing while, for example, we are drilling. We have tools that we call them major, like MWD measurement while drilling, or LWD logging while drilling. So we also have the same concept in like understanding Earth. So now let's start with what we're gonna like do actually. We have, of course, a goal. So we don't read the Earth just for the sake of reading it, right? So we generally read it for several aspects: mining, carbon capture, geothermal systems, producing oil and gas. We have several reasons behind it. But today we're gonna correlate like how we read Earth to three major goals. The first one is carbon capture. Second one is geothermal systems, and the third one is the gas storage. So basically, we need to first understand what is carbon capture and how we store carbon, right? So, for example, we're gonna have this system. This system has natural gas. We extract it, we produce it, right, into these power plants, and these power plants will get some sort of CO2, right? And we now try to do some sort of like technology that captures carbon and separate it from other emissions. And that's the part that we are not going to discuss. The thing that we're going to discuss is we are trying to store this carbon because basically what do you expect like as a major problem that we generally say. For example, we cannot produce gas and store it, right? So why can't we store gas? Like anyone might have an idea.
So I believe the just few countries can really have this technology in the sense that, at least as far as I know, it's an expensive technology and it's required a huge amount of the electricity. So I would assume the probably countries as Iceland, maybe Denmark, and also it's here written the under the North Sea. So the North Sea, it's definitely the north part of the Europe. So the probably Scandinavian countries.
Yes, so generally, as you said, we cannot store gas because it's a very expensive operation. We cannot do it on the surface. So the same goes with carbon dioxide. We should store it underground, especially when carbon dioxide is not something useful, right? For example, gas is useful. We might sacrifice the amount of money to store it on surface if we don't have, for example, the correct formations that we can store it underground. But for carbon dioxide, it doesn't make sense. So that's one goal that we need to achieve by reading Earth surface, by reading Earth internal subsurface. So, and that's also another illustration, shows how this process works. Now we capture it, we can transport it, and then we can use it in some industries, and later we can store it if we don't need it. Um, Also, there is very interesting technique, but it is not like used in today's technologies because it's not really effective, and also it has some concerns. We basically, instead of storing it underground, we're gonna pump it under the sea, under the ocean. So we have like three stages basically. We have the horizon pump. Um, we're gonna pump it in very like light surface and very light depth. But like this is very, of course, concerning because it might leak to the outer layers. Other type is we're gonna pump it inside the ocean in very low depth, in very high depth. Sorry. So what will happen is because if you go deeper and deeper in the ocean, you're gonna have an increase in the pressure. So the CO2 instead of being in gaseous form, it will turn into liquid form. And what will happen actually is when it turns into liquid form, it's basically heavier than water. So CO2 in liquid form is heavier than water in liquid form. So it will settle down on the ocean floor. And again, there are some like illustration as well that tells you where we can like store the CO2. So for example, in abundant fields that the field had, for example, hydrocarbons, we got them out, and then we are pumping what? CO2. That works very well. We have the salt formations, and that's very interesting idea because, for example, some formations might be salty, and we pump into this formation some sort of dissolving chemicals that dissolves the salt. And what will happen afterward that it will create cavity. And the best part of this is this cavity is very strong and very well structured. So if you pump CO2 inside these cavities, it will remain in a stable condition. And also we can pump it inside the aquifers. Aquifers are basically the water that's inside the earth, the underground water. And this water has also some sort of salt. And when you pump when you pump the CO2 inside them, it will be dissolved in the water. But this also creates some issues because they might create some precipitations, like they can create some salty or carbonate rocks that can basically block the pathways of these aquifers. And basically, if you are trying to have this system for like more sustainable goal, for example, 40 years, 30 years, putting the carbon into these aquifers, and the result will be blocking these pathways. You cannot do this kind of stuff because if you want it to be sustainable for 30 goals, this cannot happen because basically your system is plugged and you cannot pump any more CO2 inside. Um, Now we gonna discuss this picture. What's burning in this picture? Can anyone say?
So probably this is the gas, I would say maybe methane, and
Ex-
probably we pump the oil out of the water, and the methane is a subproduct.
exactly as you said. So basically, if we are going to drill for exploration or for production, what we're gonna have basically is gas. Um, because generally, if you have oil, you're gonna have gas. Also, you're gonna have water in the system. But that creates an issue because, as we've been discussing before, when you get natural gas, you need to have like strong facilities that can handle the production of it. So if you are at the middle of the sea, you cannot have like surface facilities that can transport the gas and move it to storage tanks. No, you cannot have this. So we're gonna burn it. So this kind of thinking is not very effective, right? Um, so what we try to do is basically putting this gas again inside, right? So like assume this is not CO2, okay? Assume it's gas. So we're gonna produce the gas, for example, move it to a reservoir. It doesn't like need to be abundant reservoir, maybe a good sedimentary formation. Then we pump it inside instead of like just burning it away, right? And then we have the geothermal systems. Geothermal systems, we have discussed them before. Um, for example, you pump water inside. The the inner layers of the earth are high in temperature. This water will get heated, might turn into steam. We pump it up, and then we move it into turbines, and then this water will lose its energy, which is heat basically. It will cool down. We will move it down again and circulate the system forever. Not forever, but like for a long time. And one thing that I forgot to mention about the CO2, for example, we're producing oil and gas, right? We need to produce gas because gas is more sustainable than oil. It has less emissions, less harmful emissions. So we're gonna produce this gas. We're gonna store some of the CO2, and sometimes we can do enhanced oil and gas recovery. What does it mean? So basically, when you produce gas and when you produce oil, the internal pressure of the rock gets lower. Makes sense, right? Because the pressure inside was high because the gas and the oil was kind of resisting this rock and creates more pressure against it. So what will happen is when you produce a lot of oil, a lot of water as well, a lot of gas, this pressure will decrease and your production as well will decrease. So what you're gonna do is you're gonna pump or let's say inject CO2 inside. So you're gonna increase this pressure again and you're gonna have good production. Does that make sense?
Yeah, I mean, for sure. I mean, it sounds like realistic.
Yeah, it's very, very basic idea. And now there is a question. If you have offshore rig and you have, on the other hand, onshore rig, um, now which one do you think like required more surveying, more readings, more time before we drilled these wells? The offshore,
You mean for the exploration, right?
yeah, which one required more exploration? Because we cannot just drill. We need to
Mhm.
explore. We need to read, right? So which one requires more readings?
Um, so I think probably because the huge amount of the water is not explored yet. So probably it's easier to drill in the water because probably it's not such deep layer, but could be that it's more complicated to find out the place. So I would say that onshore it's easier to find out.
Exactly. So it's as you said, generally, but the main problem that we have in water is the amount of money we're gonna need to drill a well, right? So, for example, onshore, the amount of money is maybe 7 million to $10 million. But if you talk about the offshore, the amount of money which are required rises to 50 to maybe 100 or $200 million just to drill one well. So of course, before you're gonna decide where you're gonna drill, what is the depth and what are the other stuff, you need to have more certainty. So here, the level of certainty is not as important as here because, as you said, in water is harder. The logistics are harder as well. You're gonna need to have like literally floating rig on the water surface. That requires a lot of money, and you cannot really sacrifice that money and go drill without any certainty. You need to be certain about where you're gonna drill exactly. And now we are going to discuss the three layers of investigation. The first layer is correlation. Again, the same as you were like trying to understand a human body by saying, for example, I feel pain, I see skin color changes, I have swelling. We do correlation with the earth. So we might say, for example, we have this region. It's kind of built. That's going from like Algeria to Iran. So we would say it's more likely to have hydrocarbons in this region, right? It's not only also about hydrocarbons. It is about we more likely can have good reservoir properties. So what are the properties of reservoirs? Two properties: permeability, which is the conductivity of if you have a fluid inside the rock, how like would it be able to move from like place to another one? That's permeability basically. And you have porosity. Porosity is the amount of space you have inside the rock. So if you have more space, you're gonna have more hydrocarbons probably. So we're gonna say, for example, that along this region, we are having more chances of getting a reservoir and getting hydrocarbon storage. We might also do something else in correlation. You know that theory that says the plates of continents were intact and then they started separating. That theory kind of makes sense because, for example, if you look at this picture, look at this coast, for example, on this coast, we know that Nigeria, for example, had oil. It has also gas. We know also Luanda. Oh no, Luanda is the capital. Angola, for example, Cameroon, um, and this region has hydrocarbons. Also, if this theory is correct, then Guania, Guania, and Suriname, there should have also hydrocarbons. And that actually was true, basically. Like Shell and some other companies tried to explore the region, but unfortunately they had dry wells, which means they didn't have any production. But ExxonMobil, for example, on the other hand, they tried to go further and further, and they could produce. And before 2015, Guyana had zero production of oil. The country had like zero clue that they may be able to produce, but after the ExxonMobil efforts, they could produce oil, and that's all related to this theory that we say, for example, since Nigeria has oil, and since they were in the same place, basically, like Guyana, Suriname, there should be hydrocarbons, right? Um, Also, do kind of correlation for the temperature. I don't know, the picture doesn't really, it's a bit blurry, but like for example, as it gets reddish, as it means that you have more temperature. So for example, let's say this depth is 4,000 meters for all this reading. So we're gonna say if you want to have a geothermal system, it's gonna be probably in the west coast of America. If we need to have a geothermal system, it's gonna be probably near to Djibouti, Somalia, and Yemen, maybe close to Indonesia, Philippines, right? And some the east coast of Russia, for example, maybe Japan and Turkey. And that actually makes sense because now if we talk about the geothermal systems that we have, they all are located in these regions, like Kenya, for example, the west coast of America, Turkey, Philippines. But for Indonesia, it didn't happen because they didn't work on it that much. Also, Iceland, for example. So correlation is the very, very first step to start like doing the other layers of investigation. It is where we can locate the area of interest, basically. And now we are going to do something further. Now we need to really understand, is this region is capable of, for example, carbon capture, carbon storage, gas storage, or producing gas, or to be a good geothermal reservoir. So what we're gonna do is basically doing some testings, right? We have at the beginning two important testings. We have gravity and we have magnetic surveys. So how they actually work? So for example, we have gravity. Let's say we are scanning a specific depth. While we are scanning, we say, for example, this gravity is high. Okay, that's good because we have granite and it's still high. This actually means represents density basically. It represents density. So suddenly it gets dropped, right? Because of this rock. This rock, as you see, is less dense than the granite. Granite is 2.6, this one is 2.0. So we're gonna have increase in gravity. So understand that the density here is lower. On the other hand, you might go with lower density, 2.6, and then you reach this rock, for example, and that's not a rock. We call it like it's kind of again like a build. It's like for example there was a cavity and this rock was igneous rock, which means it's made out of magma. It's too heavy and too dense, so it goes like trenches inside the rock formation. So we can understand that we have this kind of formation because the density increased. We understand that this rock is dense, exactly, and we might know that we have a fault. How we do that? And the faults are very important because they actually like tell us the boundary of our system. So, for example, we might have a basin, and we might have a reservoir, after like surveying the basin. And then you might have a fold. This fold generally moves a layer of the rock up and a layer of the rock down. And this can usually create kind of like discontinuity. So literally, left side is discontinued from the right side. So if you have, for example, aquifers, if we have hydrocarbons, if we have gases inside, or if you are planning to store CO2 inside your rock, you're gonna understand that since there is fault, my CO2 cannot move because it is dissolved in aquifers, and the aquifers basically cannot move because there is fault. So how do we know that? We know it from the density changes. Now we need magnetic surveying. Why is that? Because sometimes we might have kind of rocks that has low density, but we cannot really like differentiate them from the sedimentary rocks, from the shale, and from the the tight rocks, rocks that has no pore spaces. Like for example, the ore body. The ore body is basically um, kind of formation that contains a lot of minerals. It is very tight. Its porosity almost zero. There is no permeability, so it is very um, risky rock. Like if you drill inside it, you cannot have anything because it's already like impures. It has no spaces inside. It cannot contain water. It cannot contain oil or gas. You cannot pump CO2 inside it. You cannot have geothermal inside because it cannot really contain any fluid. But how we do know that when its density is not very high? We're going to understand it from the magnetic field. So since it is rich in minerals, it will create a magnetic field that we can read, and we can understand that, okay, the density might be a bit lower. Okay, this is getting a bit higher, but not as much as the magnetic field, right? And then we're gonna understand that, okay, this rock is basically impervious because we understand its type. Its type is ore body. And now we do seismics. So does anyone have an idea about how we do seismic surveying?
I never heard about this, so maybe you could tell.
Ah, okay. So seismics are basically we are doing pulses on the surface of the earth, and these pulses are traveling. They are kind of sound waves. And as you know, the property of sound that if you have a solid material, the sound will go faster inside it. Like the denser the material is, the faster the sound will be. Um, and for example, if you have lighter material or lighter material, the sound will move slower. So how does that make sense? Basically, if we want to say, for example, or to distinguish whether we have hydrocarbon, whether we have water, for example, whether we have gas, what we're gonna do is doing seismics, right? Because if we have gas, you understand that if this wave goes inside it, it will move very slower than the other fluids. If it moves in water, it will move faster, and then you're gonna understand, yeah, this is gas. Okay, this is water. All right, we have kind of like a working system. We understand that because we have gas on the top, we have oil in the on the mid, we have water at the bottom because of the density changes. And also we can get kind of like porosity out of it. So if you have, for example, porous rock, we understand that these waves will also be slower. The same sense of gas and so on. So we also do electromagnetic surveying. Why we do it? Because usually, okay, you're gonna do seismics, you're gonna do the gravity, you're gonna do the magnetic, but also you want to make sure that these hydrocarbons or these gases or this water is existing, right? So we're gonna do this kind of testing because if you have water, aquifers, they are more conductive, right? If you have, for example, oil, they are not conductive, basically. as much as the aquifers, of course. And for example, if we have tight rock, the tight rock is not conductive at all because it contains nothing. It is basically solid rock. And also, it is very effective for geothermal systems because if the water is hotter, then the conductivity will get higher. So we can understand that the temperature in this region or at this depth is that much because it emits this amount of conductivity, or it shows us this amount of conductivity. And also we do some sort of surveying as well. Like this surveying is more related to like some more specific parts of the migration of oil and gas. It is not related to geothermal or the hydrocarbon capture or the CO2 capture, but we need it if we need to understand whether we're gonna have in this basin rock or gas or oil, because sometimes the gas or the hydrocarbon is not matured yet. It needs to undergo some amount of heat, some amount of pressure, and then it gets matured, and then it turns into gas or into oil. So how do we know what kind of hydrocarbon it will be? We generally do some testings like TOC. TOC is the total organic matter. So, for example, we might find it lower here. That means this is reservoir because reservoirs generally, as we've been saying, they are porous. They are basically sandstones, right? So sandstones generally contain like oxygen. So if you know that it contains oxygen, there is no organic matter that can survive these conditions. So we understand that it is porous, it has a lot of water, and so on. Well, if you have rich organic matter, you're gonna understand that it lacks oxygen. We call it like it is lower energy system. So we have very good preservation conditions for the organic matter, and we understand that that's probably shale because shale doesn't contain oxygen, for example. And this kind of like these things you're gonna have, for example, the ratios between EC and AL, the CO and AL, MO, and that kind of like mineral ratios that we can do some correlation afterward. And we are moving now to the third stage of investigation. Now we understand, for example, the type of the rock. We can estimate it based on what? Based on the gravity, because gravity tells us the density, but also the magnetic surveying, because also the magnetic tells us the amount of minerals that this rock contains, and then we can say it is igneous, it is metamorphic, or it's sedimentary rock. Uh, and then we do the seismics, right? Seismics tells us whether it contains pore spaces, whether or it doesn't, whether it is gas, whether it is aquifers, like as we've been saying, it's water, for example. Um, and afterwards, we're gonna do, for example, the electromagnetic surveying that tells us the temperature of these aquifers, and also like acknowledge our previous assumption that if we have like slower seismics, then we have fluid inside. Same thing, if you do the electromagnetic surveying, you're gonna understand, yes, this is actually true. And then we move to the third layer. I just wanted to have a review about the previous layer. So in this third layer, we're gonna drill. So why we do all the previous stuff? Because drilling is actually very expensive. We have discussed this in the geothermal webinar, and we understood that drilling sometimes costs about 50% of the total money that we're gonna spend to have geothermal plant. So, anyways, let's start with very basic ideas about this layer of investigation. So this is actually called shale shaker. We're gonna drill, right? Because, by the way, the second investigation layer, we are assuming, we are not sure about anything. Like lots of projects ended up having dry wells. So if we have dry wells, that means sometimes this second layer is not enough. So we're gonna drill to acknowledge and to understand more and more about the reservoir properties. And that's one thing. We're gonna drill, and while you're drilling, you're cutting rock. This rock, you're gonna get it up by some circulation of the drilling mud. You don't need to know how this works. But anyways, we get sort of samples of these rocks, and then we can understand the mineral composition of it. We can understand its type, whether it's shale, whether it is sedimentary rock, sandstone, dolomite, limestone, or whether it is igneous rock, like for example basalt and granite. Because basically, if we have basalt, for example, you understand that the drilling is gonna be harder, and based on that, you need to prepare yourself for the other wells. We also do something called core blogging. So we are drilling, but that's very expensive. A lot of companies don't do it. We're gonna get some core samples, and these core samples are like gold for any drilling company, or for you if you want to know the properties of your reservoirs. Again, if you want to have geothermal, if you want to store gas, if you want to store CO2, these are like gold for you, because you can understand the porosity, you can understand the permeability, you can also, of course, understand the mineral composition, the type of the rock, a lot of properties. You can get it from these samples, and generally, at least like in any reservoir, you're gonna have to get some of these samples. Um, and then we do some tests, as you can in the picture. We have the density neutron. We have several tests here, but I would suggest to start with this picture, for example. So we have gamma ray. Um, I'm just asking, you know, what kind of rocks or minerals do you think that emits some decays, some radioactive decays?
Um, so as far as I know, we always have some radioactive elements in the ground. So which came from the space or whatever. So and probably it's stored inside of the some ore, like so probably in stone we can find some radioactive elements together with the like iron ore or any other metals.
That's very close. So basically, iron has the magnetic field. For radioactivity, we generally have like uranium, potassium, and thorium. And so that's very interesting thing because again, the more you know about Earth, the more accurate you're gonna be. For example, we're gonna read these emissions, and you see here it is high, right? And then it decreases. So, for example, this is the scale from 0 to 100, and this is the depth. So, at this depth, it is high. At this depth, it's low, which means there's something. Makes sense, right? So, what's happening is we have here more uranium, more potassium, and we understand from our like previous knowledge that if we have shale or clay, it is a rock that's very porous, but it is very impermeable. So you cannot produce anything out of it, and you cannot store anything. But it is very porous. Um, but it indicates some other stuff. We're not gonna discuss it. So we understand that this is shale and this is sandstone, because sandstone doesn't have the same composition, doesn't have, for example, higher concentration of uranium, potassium, or thorium. So understand that that's basically the sandstone region. And this is the dipping angle. So what does mean dipping angle? So for example, sometimes we have layers, right? So that's basically a layer. That's basically a layer of shale, and that's a layer of sandstone. But sometimes these layers are dipped into some angles. It might be dipped like straight, zero angle. It might be dipped like this. Might be dipped like that. Might be dipped like this as well. So these dipping angles also provide us some information about the drilling hardness. So if they are dipping straight, then you're gonna drill easier than if they are dipped like vertically with 100 and 100 plus degrees, right? Um, Sorry, yeah, with 90 or with 90 degrees, for example, if, like they are dipped like that. This is like 0 degrees. This is 90 degrees. Anyways, and we also do some resistivity logging. So what we actually do is, I would show you a picture that might contain some information. Yes. So this is the resistivity. So this is, for example, hydrocarbon. It is very resistive. And we also knew that since we have hydrocarbon, it means that it is less conductive, right? So we understand that this region, it is hydrocarbon. We understand that for example, this region is brine. Brine is aquifer that contains a lot of salt. So since it's salty, it is resistive, right? So yeah, it is conductive. So its resistivity would be very low. Makes sense? And the same thing goes for the gamma ray again. If the gamma ray is high, it is shale. It is if the gamma ray is low, then it is sandstone. And we also do something else. We call it the caliber log. What does it mean? We basically drill a borehole, and while we are drilling, we might have some fracturing. Um, so some of the rock actually get fractured and makes the borehole a bit like wider. Sometimes we have something called mud cake. It's literally a cake made of mud. You're gonna usually find it in like if you're dealing with sand, for example, or shale. You also have it in shale. Like it doesn't really mean anything, but it tells us something very important. The certainty of our readings cannot be assured. So if you have a mud cake here and you have gamma ray readings, you cannot be very sure whether or not it is shale or sandstone. Why is that? Because mud cakes are basically some of the mud that we pump inside, and this mud usually contains potassium. And since it contains potassium, it might increase our readings because we already know that potassium is a mineral that emits some radioactive decays. So since it increases our readings, we cannot be assured about anything. We cannot tell if it's sandstone or it's shale. So we do further tests to be more certain, right? We do something called density and neutron logs. So how does it work? Density is the same thing. We uh, merge some sonic waves, literally like the sound waves, goes inside the rock formation. The denser it is, or the more porous it is, the more porous it is, it will be slower. The denser it is, which means less porous, it will be faster. That's one thing. Also, we're gonna do neutron. Neutron is a tool, like we emit neutrons, literally, and these neutrons, for example, will collide with hydrocarbons, and we understand that hydrocarbons are literally a series of CH. CH is carbon and hydrogen, basically. So we understand that hydrogen is made out of one atom, made out of one neutron, and when this neutron collides with it, then we understand that there's gas, or there is hydrocarbon, which is oil, or maybe there's water, because water as well, it is H2O basically, right? So we can tell whether or not there is a fluid trapped, and based on that, we can tell whether or not we have pore space or not. So, for example, we have here shale. So what happens is we have higher density. Shale is actually dense, even though like it is not, it does not appear dense in the seismics because here yeah, so here the shale is dense out of other fluids and out of gas, out of trapped fluids and that kind of stuff, so it appears denser. But if you are doing it from the surface, it will appear smoother because we understand that it contains fluids inside. And also, if you look, we have the neutron. The neutron is actually the amount of porosity that we have. So it shows us that it's very porous, right? But that doesn't make sense. Why is that? Because this kind of porosity is not something that we can produce. It can be porous, but it is not permeable. So at this region, we understand that sand. The sand is light than shale, and also it is less porous, but we can produce it. We need sand because of the permeability. It is more permeable. And then shale goes again, the same pattern. And then we have a region where there's gas. If you have gas, the nitron will show us that we have a huge cavity, right? That makes sense because gas is not as dense as any other liquid. If we have liquid, it will show us that we have lower cavity, and then we have shale again. And yes, to make sure that our readings make sense, we're gonna also read the resistivity logs. So we're gonna read it. Okay, there's hydrocarbon here. That's basically the gas, as we've been saying, for example. Yeah. Oh, sorry, I made fatal. I mixed two things together. Again, this was the density, and was the neutron in the last picture. I mixed them together. So let's move on this picture. So here the density gets higher, right? Gets lower, sorry, because there's gas, there's a lot of cavity, and the neutron log gets lower. So it means that our neutron readings that are colliding are lower because that gas is basically less dense. So the amount of neutrons that are likely will collide with other neutrons will be lower. This like separation gets tighter when it goes to oil. We understand that our density is getting higher because oil is more dense. Our neutron will also be closer to our density reading because oil contains more hydrocarbons than gas. So if you like emits a neutron, it is more likely to collide inside the oil more than the gas. And same goes with the brine because it is the most dense fluid among all of them. Yeah, and that's also like some explanation of the sonic waves. So sonic waves also gives us density as well. Like the more time you have, the less density that you have. The smaller time, like the faster it is, the more density that you're gonna have. That's also an explanation of resistivity. If this is permeable, then you have high resistivity, and so we call it the spontaneous. It means like the voltage. So, for example, you might have higher resistivity, but you might have high voltage. It means that no, you have salt, you have aquifers. On the other hand, you might have, for example, lower permeability. So the resistivity is not as high as the high permeable. But the voltage will be again high. You might have impermeable. So here there's tight carbon or sandstone. So we understand that the resistivity is high because again it is impermeable. And if it is shale, then you're gonna have higher resistivity because literally shale يعني, made out of a lot of water and aquifers, which means that you are getting more conductive. And yeah, and the voltage is not high because again the voltage is like we gonna measure between a point to another point. So for example here, a point here has like lower aquifer amount or lower conductivity, and this region has more conductivity, which means there is big voltage. But here all the region has higher conductivity, so literally the voltage is not as high as the like if we have a difference between more conductive and less conductive region. We do some sort of correlation. Again, the picture is very, very blurry. For example, we have one, two, three, five wells. We produce these wells from different between them different distance. So, for example, we see in this well This is gamma ray. We understand that's probably shale. That's probably sandstone. That's maybe something else. That's probably sandstone as well. We see the same pattern, right? So we see this pattern shifted from here to here. This pattern shifted from here to here. This pattern, again, the same thing. So we understand that, okay, this layer, if we have a drill to drill here, we understand that at this depth, we're gonna have this formation. At this depth, we're gonna have change in formation. So this kind of correlation is very important. If if you are like required to drill more wells for production, basically. And also in this picture, we're gonna have very interesting imaging. Sometimes we understand that we have faults or fractures. And fractures generally means we have permeable cavity inside the rock, right? Because there is no rock, basically, there's fracture. So how we can make sure that that's actually happening? We do some imaging. Like literally, we go inside the borehole and we take images. These images also can tell us whether we have shale or whether we have sandstone, like in this picture, for example. Like the darker it gets, it means that it's shale, because shale mainly is contained out of fossils, out of organic matter. So it's darker on this scale. Here as well, we're gonna have shale. Maybe this region, on the other hand, it may not be shale, because generally you don't have thick layer of shale and then you're gonna have very tight layer of shale and sandstone. That's probably fracture. And again, since it is too dark here, that, yeah, tells us that's probably a factor. Um, and also one last thing, um, when we want to like produce anything, as we've been saying, geothermal, CO2 and the gas, we do reservoir simulation. So we gather all the information that we got. We first create static model. Static model is like there are no dynamics. We understand that the fluid is trapped inside. It doesn't move. And then we're gonna have dynamic model, because we're gonna produce these hydrocarbons. But this happens after we do our exploration wells, after we understand and confirm that we are actually having, for example, sandstone, we are actually having porosity, we're having permeability, we have gas inside, we have high temperature if we're talking about geothermal energy. And what we do next is something called history matching. So we're gonna start producing. We have good information, but this is not enough, right? We need to do some seismics, and that's what we call 4D seismics. So instead of like getting, oh, I forgot to explain it. So for example, this is 2D seismics, because it is like this axis and that axis. That's why it's 2D seismics. This is the distance that you are moving, and that's the elevation. Now we need to do 3D seismics. And that's 3D seismics. So we have this distance that we're moving, that direction, and we have several sensors here. So which means we have actually this dimension as well. And we are calculating it like as elevation. So we're gonna have 3D seismics. Now the 4D is when we do it with like time separation. So for example, we did this in July. We do it again on let's say August. We do it again on September. We do it again in November. And that's the 4D seismics. And they are very important to do um, like the reservoir simulation that I have been talking about, the dynamic model. After you do the dynamic model and after you gain production, we need to go further into production, right? So what we do is we're gonna compare our results that we had from the simulation into our results that we had in our real life. And we do something called history matching. So if there are changes, like significant changes, we understand that our information are not correct. That's why our simulation did not perform well, and it was not like close to our real values. If the values, and then we need to do adjustments, or maybe we need to investigate further. Now, if our values are similar to our like if our real values are similar to our simulation values, then we understand that our history matching is doing well, and then we will do something called forecasting. Understand the model that we had in the simulation is correct, and we can do forecasting. We can, let's say, assume or let's say predict other wells elevations, other wells locations. And we understand that any value that we will get is correct probably, and hence we can go further and do, for example, simulation for injection of CO2, as we've been discussing in the first slide. Or maybe we can do something called hydraulic fracturing. Again, if you have shale, the shale is impermeable. So how we make it permeable? We're gonna fracture it so we can get the oil or gas that's inside it. Or maybe if it is very compacted zone or it's tight sandstone that's impermeable, then what we're gonna do probably is we're gonna fracture it as well, so we can have geothermal system. Because usually, if you are going deeper and deeper, we are going to reach something called the basement, and the basement is generally made of igneous rocks, which are granite, which are basalt. These are very tough rocks. They are very tight. They cannot really contain any fluid. So we're gonna fracture these rocks so we can contain the fluid and we can circulate it from the surface to the bottom. Thank you very much for your listening and for your contribution. I would be so happy if you have any questions.
Thank you again for the giving your presentation. I would just like to ask one question because I already got a lot of information, just to be sure. So about the storing technologies, like for the carbon dioxide, you mentioned that we could liquefy this and store under the water, right? Because it's heavier than regular water. Just to be sure, like in which condition should it be? Like, should it be like really frosted, or like, so how it doesn't become gas back?
Yeah, I can explain. So I think, oh, sorry. I think you mean um, this picture, right?
Yes, yes, exactly.
Yeah, yeah. So how we make sure we're gonna like pump it in very deep elevation. So let's say 5 kilometers deep. And that means, like, for example, if you're going deep in the water, the pressure gets higher because it's the hydrostatic pressure, basically. So since the pressure is too high, when you pump the gases CO2, it will be liquefied because of the pressure. That's the same concept that we liquefy, for example, gas, natural gas, but not because of water. We liquefy it in other techniques, but that these techniques also requires very high pressure. That's how we turn any gas into liquid form. We can liquefy it, and also we decrease its temperature. So you can have like two factors in your mind: very, very high pressure, and also cold conditions, like in the basement of the ocean. Was that your question? Like, does that answer your question?
Yes, yes, this was exactly what I like to hear. Yes, now it's clear. Thanks.